a definition. I'll zoom in. So composition of functions. Composition is an operation on two or more. So I put 2 plus, but typically in this class it's 2. Two functions that form a new function. So the range of the first function becomes the domain of the second function, and that might seem weird right now, but hopefully it'll make sense by the end of this. It's written in 2 different ways. Both of those are the same exact problem. It's denoted as f of g of x or f of g of x. And this is like a little circle. It's not a O and it's not a 0. It's a little circle. And you'll see those written. In both of those, you would do g first and then f. So you put g into f, and here you put g into f. Okay. So the first problem we're going to do is this one. So given g of x is equal to 2x plus 3 and h of x is equal to x squared minus 1, we're going to find gh of 3 first, and then using the same number, I just switched the functions to show you that order matters. So let's first do a. So a is asking us to take 3 and plug it into h. So I go up here and I find h. So h of 3 is equal to 3 squared minus 1, which is going to be 8. This is equal to 8. h of 3 is equal to 8. So what we now do is you take 8, and that becomes our input for g. So we're going to plug 8 into g. So this is going to be g of 8 is equal to 2 times 8 plus 3, which is going to be 19. So we say g of h of 3 is equal to 19. And here I will use the red to say this now goes into g. So on the other one, it's the same number, we just reverse the order. So now this is asking us to plug in 3 into g. So here's g. So g 3 is equal to 2 times 3 plus 3, which is 9. So our g of 3 is the same as 9. So now this becomes a 9. We would just substitute 9 in for this. So h of 9 is equal to 9 squared minus 1, which is 80. So h of g of 3 is equal to 80. And so using the same numbers and the same functions, what this one shows is that order matters. So we're going to put that on here. We'll write order matters. Okay, so which one goes first definitely plays a role in your correct answer. Okay, so that's when we're given numbers. What if we're just dealing with functions? So if we're just dealing with functions, here's the next problem. Find f of g of x for f of x is equal to 4x plus 5, and g of x is equal to x squared minus 6x plus 2. That's plus 2 right there. So in this problem, this is asking us to plug g into f. So this actually whole thing is our input into f. So f of g of x is equal to 4, but instead of x, I'm going to plug in g of x. So my input is going to be x squared minus 6x plus 2 plus 5. Plus 5. So this is 4x plus 5, where my x was g of x. And then now you would just simplify. So we're going to distribute, which gives us 4x squared minus 24x plus 8, and then plus 5. And then we would combine our like terms. 4x squared minus 24x plus 13. And that would be your answer. Okay. Next one. Given p of x is equal to 5x plus 2 and m of x is equal to 3, solve m of p of x is equal to 51. So in this problem, I didn't tell you what to plug in, but I told you the answer was 51. So we're going to ignore 51 and we're just going to set this up. So this is the second way that was in the very beginning that we wrote it. G goes into F. So in this case, we're going to take P and plug it into M. So P is going to be plugged into M. So that's going to be 3. And we're going to plug in this into that. So 5x plus 2. So that is m of p of x. And now it's equal to 51. And now you would just solve for x. So we would distribute, which gives us 15x plus 6 is equal to 51. Minus 6 from both sides, so 15x equals 45. Divide by 15, and we find x is equal to 3. So m, and then a little weird circle, p, m of p, of 3 is equal to 51. And here, just so it's in our notes what we did, we plugged p into m. So we plugged p goes into m. Okay? And so this definitely relates to inverses. It's used to prove inverses. So that's what we're going to show right here. So given f of x is equal to x plus 2 squared minus 5, and g of x is equal to the square root of x plus 5 minus 2, we're going to show their inverses using composition. To show inverses, you actually have to show both directions. So we're going to plug g into f, and then we're going to plug f into g. And if they are inverses, what you plug in should be what you get out. So you should be left with no math. What you plug in should be left with what you get out. Okay, so here we're going to plug g into f. So this is going to be plugged into f. So f, and then instead of x, we're going to plug in g. So square root, and I'm going to write small, x plus 5 minus 2, that's my x, plus 2 squared minus 5. So just let me go through this real fast. X is the red, plus 2 squared minus 5. Okay, and now you're going to simplify. So to simplify this, negative 2 plus 2, those will cancel out. So you're left with the square root of x plus 5 squared minus 5. Squares and square roots cancel each other out. So we're left with x plus 5 minus 5. And the plus 5 and the minus 5 cancel. So we're left with just x, which so far, half of our problem is done. We got out x. So this is true. When I plug g into f, all of the math cancels and we're left with x. So now we have to do the other way. We have to plug in f into g. So we're going to start with g, and this is going to be our input. So square root. My x is going to be f. So we're plugging f into g. X plus 2 squared minus 5. I'm still under the square root with the plus 5, so that's my x, plus 5 minus 2. Okay? So what we can do first is the plus 5 and the minus 5 will cancel. So we've got square root of x plus 2 squared minus 2. And then the square root and the square will cancel. So we've got x plus 2 minus 2. And the plus 2 and the minus 2 will cancel, so we're left with x. So these two are, in fact, inverses because of the x. I will say, though, if you graph these, you will have to restrict the domain on f of x, okay? Because square roots don't have negative answers. Okay, last ones are other operations. So if you did ones where you plug them into each other, there are other operations. So we're going to do the 4 different operations with these 2 functions. So given m of x is equal to 2x plus 1 and n of x is equal to 4x squared plus 2x, we're going to add m of x plus n of x. So my m of x is 2x plus 1. And I'm going to add n of x, which is 4x squared plus 2x. And all you have to do with this one is combine your like terms. And you get 4x squared, 2x plus 2x is 4x plus 1. So just combine your like terms, that's it. Subtracting is similar, except you need to be careful because it is subtracting. So if we do m of x, 2x plus 1, and we subtract, and here's where it gets a little tricky. You're subtracting all of n of x. If I just write here 4x squared plus 2x, this is not correct because I would only be subtracting the 4x squared. I have to subtract all of n of x, so I need to put it in parentheses, which means you need to distribute the negative. So we've got 2x plus 1 minus 4x squared. My whiteout from earlier when I made a mistake is making this wonky. And then minus also 2x. Now you can combine your like terms. I typically write my x squareds first. So I've got negative 4x squared, 2x minus 2x. Those actually canceled. So plus 1. Now we're going to do the product. The product is when you just multiply them. So m of x, which is 2x plus 1 times 4x squared plus 2x. You guys can do it any way you want. In this class, normally we've stuck with the area model. So I'll do it down here. So 2x plus 1, 4x squared, and 2x. So I've got 8x cubed, 4x squared, 4x squared, and 2x. So if I combine my like terms, I've got 8x cubed plus 8x squared, because these are our like terms, plus 2x. That would be your answer to that one. Division is a little tricky, and this problem is a good one. It has something that I haven't taught you guys yet, but you know, it's nice to see something in advance. So with division, m of x divided by n of x. So m of x would go on top, 2x plus 1. N of x would go on the bottom, 4x squared plus 2x. A lot of the times with division, you're then done, except you have to say what your x can't be, because you can never have 0 in the denominator. So since we have an x squared in the denominator, I'm going to go ahead and factor that. So the top is 2x plus 1 over the bottom. I have a GCF of 2x, so I'm going to take out a 2x. And if I take out a 2x from 4x squared, I'm left with 2x. If I take out a 2x from 2x, I'm left with a plus 1. So here, we're able to figure out our domain can be any number, except x cannot be 0, and x cannot be -1 over 2. When we get into simplifying rational